Hello class, today we're going to cover section 3.3 Trigonometric Equations, and so let's just jump right into it. So this first problem is asking us to determine whether pi over 4 is a solution for the given equation, and then also checking if pi over 6 is a solution. So in order to do this problem, what we need to do is substitute in. So we're going to go 2 sine of pi over 4 minus 1, and then we're going to check to see, is that in fact equal to 0? Well, 2 times sine of pi over 4, we know that pi over 4 is radical 2 over 2 minus 1, and that's going to be radical 2 minus 1. Is that going to equal 0? The answer is clearly no. And again, how did I get this to be this? I used the unit circle, but I've used the unit circle so much I've memorized it, and I'm sure eventually you will also. All right, so let's do pi over 6. So 2 sine pi over 6 minus 1, is that equal to 0? So we know that pi over 6 is 1/2 minus 1. We see that 1 minus 1, and we see that 0 is equal to 0. So yes, pi over 6 is a solution. Okay, our next example is for cosine is equal to cosine theta is equal to 1/2, and again let's remember that cosine of theta is equal to x over r. So then when I go to graph this thing, it's 1 and 2, so 1 over 2, and so x is 1 and the radius is 2. So whatever the radius is, it's going to hit somewhere like this. And we see that this is 2. This area from the origin to that is 1. And this is 2. So where is cosine equal to 1/2? It occurs at pi over 3 and at negative pi over 3. Not at negative pi over 3. And why is that? Because, yes it does. I'm sorry. At negative pi over 3 it also occurs. But negative pi over 3 is the same as doing a full loop around. That's equal to 5 pi over 3. And the way I did that was I went 2 pi minus pi over 3. And that yields 5 pi over 3. Now, to find the solution to this, we have 2 solutions. So we have theta is equal to pi over 3, but we have to remember that this angle here is going to be equal to going all the way around and then coming there too, because it's going in loops. So because it does that, we can make full loops around, which is 2 pi, and then we need to multiply it by k, and k is the number of times that it's gone around. So that's one set of potential answers. The other set of potential answers is at 5 pi over 3 plus those same rotations. And so what would happen there? The initial angle is from here to here, but then again we can get there by going a full oops, I didn't want that, let me cut that. By going a full loop around and getting to it. And so you can see the k here and the k here are the number of times it's gone a full revolution around. So these are the 2 solutions for this problem, it's going to be pi over 3 plus 2 pi k and 5 pi over 3 plus 2 pi k. And that's just, again, every time you do a full circle, you end up back in that same spot. All right. Here's another example. In this example, we see that there is a bit of a restriction, and so we need to pay attention to that restriction. So 2 sine of theta plus radical 3 is equal to 0. So we're going to try and see if we can solve for theta. And we end up finding that sine theta is equal to a negative radical 3 over 2. And we have to remember that we're talking about a full circle, and so the radius of this is going to be 2. So that's the radius. And the y-coordinate is going to be a negative radical 3. So this would be a negative radical 3. And this here would be a negative radical 3. So we see that this can happen in 2 spots. It can happen in the third quadrant and in the fourth quadrant. And now we need to find out what that angle is. And so the way I like to think about it is where is sine radical 3 over 2? Well, in the first quadrant, I know that radical 3 over 2 for sine occurs at theta equal to pi over 3. And so to get to this side over here, I needed to add a full pi to that. So pi plus pi over 3 gives me 4 pi over 3. And so my first potential answer is 4 pi over 3. And my second potential answer over here is going to be adding another pi over 2 to that. And that would give me 5 pi over 3. But again, you have reference to the unit circle, so you can find the 2 places where sine theta is a negative radical 3 over 2. Remembering that we're only looking at one full circle around. Okay, here's another example. Again, we have a restriction of just one loop around. And so what we can do here is, I'm going to try to clean this up a little bit and see if this makes sense to you guys. I'm going to say, all right, tangent theta is equal to 1. Where do we know that that happens? Well, that happens for me at pi over 4 and at 5 pi over 4. And so I'm saying that, and I'll use a different color for this, this theta is equal to this parentheses here. And so what I'm going to do is I'm going to say, all right, theta minus pi over 2 is equal to pi over 4 for one of my answers, and theta over 2 is equal to 5 pi over 4 for my other answer. So I'm going to add pi over 2 to both sides, and that's going to give me theta is equal to 3 pi over 4. And on the other side, 5 pi over 4 plus pi over 2 is going to give me a second answer of 7 pi over 4. And those are the 2 solutions for this one. This is one answer, and this is an answer. And then for this one over here, that would have been an answer, and that would have been an answer. Okay. Now solving these problems, again, we see a restriction of one full loop. And we can see this as being in a quadratic form, like ax squared plus bx plus c. And so it's factorable. So I'm getting 2 sine squared theta minus 3 sine theta plus 1 is equal to 0. And so that would have been the same as going 2x squared minus 3x plus 1 is equal to 0, where our x is sine. And so we see that this would have been 2x and x and 1 and 1 and minus. So this is going to be 2 sine theta and sine theta and 1 and 1 and minus. And now we see that 2 sine theta minus 1 is equal to 0, or sine theta minus 1 is equal to 0. Well, we'll do the easier one first. When is sine theta equal to 1 under 1 revolution? Doesn't that occur at pi over 2? And then this other one, 2 sine theta is equal to 1. So sine theta is equal to 1/2. So where is sine 1/2? It occurs at pi over 6, and then it occurs again at 5 pi over 6. So our solutions here are these 3 answers here. Okay. One more to do. And so to clean this one up, I'm going to have to do a little bit of trig identities to it. And so I'm going to have 3 cosine theta plus 3 is equal to 2. But instead of the sine squared theta there, I'm going to use the identity. So I'm going to go 3 cosine theta plus 3 is equal to 2 times 1 minus cosine squared theta. And again, that comes from sine squared theta plus cosine squared theta is equal to 1. And so sine squared theta is equal to 1 minus cosine squared theta. That's where I got it from. And the reason I wanted to do that is because I want everything in terms of cosine in this problem. So I'm going to get 3 cosine theta plus 3 is equal to 2 minus 2 cosine squared theta. And then moving everything to the left-hand side, I'm going to get 2 cosine squared theta plus 3 cosine theta plus 1 is equal to 0. And we see that this can be factored, so I'm going to get 2 cosine theta, and then I'm going to get 1, and they're both plus. And so I'm going to get 2 cosine theta plus 1 is equal to 0, or cosine theta plus 1 is equal to 0. So when is cosine theta equal to -1? We know that that occurs at pi. So theta, we'll call it theta 3 is pi. And then over here, 2 cosine theta is equal to a -1. Cosine theta is equal to a -1/2. That occurs in the second and third quadrants. And so theta 1 would be at 2 pi over 3. And theta 2 would occur at 4 pi over 3. And so these are my solutions. And I should have put these up here in terms of theta. So that could have been theta 3. That would have been theta 2. And this could have been theta 1. Just so we have the solutions and being consistent. I hope you found this helpful. Again, if you have any questions, please feel free to send me an email or post it on this YouTube channel, and I'll answer your questions. All the best.